Hello, so in this video we will talk about two identities regarding three-dimensional vectors. The first one is the triple vector product. The first set of identity is the triple vector product identity. So this guy. And the second one is the Jacobi identity, which we will prove by using the triple vector product identity. Okay. So the triple vector product identity says that if we have A cross B cross C, when A cross B is evaluated first, and it's on the left hand side of this second cross, so then this is equal to the dot product of A cross C times B, and subtract dot product of B dot C, which is the scalar product, times A. Now note that this is a scalar and this is a scalar, and this is a scalar. Okay, so this means this whole thing right hand side is a vector actually, and we know that a cross product of two vectors result in a vector. Okay, and this is the Jacobi identity, which we will prove after we prove the triple vector product identity. Okay, so then since we are talking about the three-dimensional vectors, so then we can say that the vector A is composed of the I component, J component, and K component, which is A1, A2, A3, and similarly B is B1, B2, B3, and C is C1, C2, C3, which are I, J, and K components respectively. Okay. Also, we know the definitions of both scalar product and the cross product or the vector product, which is that A cross B is equal to this expression, which is also can be compactly written as the determinant operation. Okay. And A dot B is actually a scalar, which is A1 B1 plus A2 B2 plus A3 B3. Okay. Okay. So now let's start with the proof now. So we start with the left hand side of 1. So we are actually, without loss of generality, we'll just prove this guy here. Okay. And then the proof of the second one is similar, very, very similar. So what we do is, so in order to have the left hand side and right hand side to be equal as a vector, their I, J, and K components should be equal. Correct? So then if we say that if we can prove that all of these components are separately equal to each other from on the left hand side and the right hand side, we can say that the vectors are actually the actually left hand side and right hand sides are equal in vector format. Okay, so then if we consider only the x component, now first of all, what is A cross B? A cross B, we know that the I component is this guy, we have written it here, so this is from here. J component is this guy, you can see it here, and K component is this guy, you can see it here. Okay, okay, then cross C means that the third row will have C1, C2, and C3. So now we will consider the x component or the I component of this. So for I component, we will have this guy removed, and we will have this times this minus this times this. Okay, so we'll say minus of this A1 B3 minus A3 B1, and then we will multiply it by C3, and then we subtract this guy A1 B2 and multiplied by C2, and A1 A2 B1 and multiplied by C2. Okay, so now if I can combine the plus terms and then minus term, we note that this is plus term and this is a plus term. So I can say, I can write this one first. I can say A2 C2 B1. Now I have interchanged the order without loss of generality, just for ease, because I'm going to take B1 out in the next step or so. And that's this guy is, I can say A3 C3 B1. And similarly, for the negative terms, I can say B3 C3 A1, which is this guy, and B2 A2 A1, B2 C2 A1, which is this guy. Okay. Now I can add and subtract the same term without changing the form, right? So I can add A1 C1 B1 here and A1 C1 B1 here, although I've written it differently just because I'm going to take something common outside. Okay, so now you can appreciate that this is a minus sign. So if I add something here and add the same thing here, the expression will not change. Okay, So now I can take the B1 outside from here. So I can say A1 C1 plus A2 C2 plus AC3 A3 C3, and over here I can say B3 C3 plus B2 C2 plus B1 C1, and then A1 is outside. Now you can appreciate that this whole thing is equal to the scalar product of A and C, and this whole thing is equal to the scalar product of B and C. Okay, so then what does this prove? So this proves that the x component of left hand side, this is equal to x component or I component, whichever way you want to write it, of right hand side. Okay. Okay, now similarly you can see that this is simple algebra here. So similarly you can prove the y component and the z component, and you will be able to prove the full identity, which is, again, I will just write it here again. So A cross B C, this is equal to A dot C dot B minus B dot C. Okay, they are all vectors here. Okay. All right, so then this is the proof of triple product identity, and the next one, the other one, the for equation number 2, which is here, you will follow the similar approach to prove. So you will go for x component, y component, and z component and prove them one by one. And then this is just long, a little bit 4 or 5 steps algebra for each of these steps, but you can appreciate that this is just quite straightforward. Okay, so now what we will do is we will do the proof of Jacobi's identity using the triple product identity. So the left hand side of Jacobi's identity is, I've just copied it from here. So then this is the left hand side here. So this is the left hand side. So left hand side is equal to u cross v times cross w plus v cross w cross u plus w cross u cross v. So now this guy, if I use the triple product identity, so using triple vector product identity for each term. Okay, so for each term, so now if I do this, I will get u dot w times v and v minus v dot w times u. And you can appreciate that if I do this over here, I will get this, and if I do this over here, I will get this. Now what can I cancel? So now u, now since we can say that if u dot v, this is equal to v dot u, right? For scalar products, we know this. Okay, because this is equal to u1 v1 plus u2 v2 plus u3 v3, and this is equal to v1 u1 plus v2 u2 plus v3 u3, and multiplication, we know that it is commutative here, so that's why they are similar. So now so now know that this guy will cancel out with this guy, and this guy will cancel out with this guy, and this guy will cancel out with this guy. So we will end up with a zero vector here. Okay. So that is how we prove the Jacobi's identity using the triple vector product identity. So, so in this video, what we have done, we have proven the triple vector product identity and used that identity to prove the Jacobi's identity for vector products. Okay. So this was quite straightforward for both these identities. It's just, as I said, it's just a little bit long algebra, so be careful with each step. So sometimes if we skip one step or skip one plus or minus here, we can make a mistake here and there. But if you do it carefully, so if you do it carefully, then the chances of making a mistake can be minimized. Okay. So this is it for this video. Hope it was easy to understand. Thanks for watching. Hope you liked the video.